We are the Stevens NASA Robotic Mining Competition Senior Design Project. We have chosen an ambitious senior design project and have made exciting progress. We're seeking funding to help make this design a reality and to get the robot down to the Kennedy Space Center for the competition in May. The Robotic Mining Competition, RMC for short, was created by NASA in support of their current Artemis program, seeking to land humans on the moon by 2024. Rovers designed for RMC are tasked with retrieving icy regolith from below the surface at the moon's south polar region. NASA has created a simulated lunar surface in which the team will demonstrate their rover design. The rover will be placed at a random starting configuration and will fully autonomously navigate through a number of randomly placed obstacles, mine icy regolith from a mining area beneath a 30-centimeter layer of lunar topsoil, before returning and dispensing mine material. The rover has mass and size restrictions and needs to collect a minimum of 1 kilogram of icy regolith during a 15-minute time period. The team will score points based on how much regolith is mined, as well as bonus points for autonomy, energy efficiency, and a variety of other categories. The Stevens RMC team has generated a robust design which can be broken down into 3 major mechanical subsystems.
The drivetrain is a simple rectangular shape made out of aluminum tubing powered by 2 motors. These motors turn belts inside of the tubing which drive toward our custom-made lightweight wheels.
The mining subsystem is centered around a uniquely designed parallel 4-bar mechanism that spans the entire length of the robot. This design allows for the excavator and storage systems to be in alignment during the entire mining process. The mechanism is actuated by 2 heavy-duty electric linear actuators. The excavation mechanism consists of a conveyor belt design that rotates about a pivot point on the mining plates. This allows for optimal conveyor angle at any depth in the mining process.
The continuously revolving scoops on the conveyor belt excavate a small amount of material with each pass while dumping the mined material into the storage and dispensing section of the robot. By designing scoops to be manufactured with a single piece of sheet metal, the team minimizes part count. We plan to use CNC sheet metal bending machines for manufacture. The team is also utilizing a technology called attachment belt. Threaded inserts along the belt allow for a modular approach for the attachment of scoops to the conveyor. This design choice will allow the team to easily replace broken parts and change the spacing of the scoops during testing.
Here's the conveyor belt system which stores and dispenses the excavated material. Material is stored between the 3D printed flaps bolted to the attachment chain and the sidewalls of the 4-bar mechanism discussed prior. The material is dispensed by rotating the sprockets, moving the chain, and sending material over the conveyor belt into the collection bin.
The software the team is using for actuation control of the robot is the Robotic Operating System, also known as ROS. ROS offers open source libraries and tools for common robot functionalities such as navigation, and specialized subroutines will allow for the control of the excavator and storage systems.
The first layer of ROS nodes turn raw sensor data into position estimates. The estimates are mapped and used to make new movement data. To map obstacles, a small motor tilts the LiDAR so it can scan the ground for craters and boulders. The robot localizes using the collection bin. The LiDAR measures the visual distortion of a marker on the bin and calculates its relative position. These new position values help path planning create new movement commands.
This chart shows a detailed schedule for the project, including major design milestones and NASA deliverables up until the competition in May. Here is a high-level breakdown of the current budget for the team to construct its final robot in time for the competition. The team has already secured raw materials, tools, and equipment from last year's team, but there are a variety of parts that are unique and need to be purchased. In addition, the team will need to pay for transportation of the robot to Florida, as well as construct a test arena. The team has already secured $2,700 and is currently in need of $2,560. Thank you.